So I want to keep it as interactive as possible. Feel free to ask me questions. Let me tell you, I'm not the data scientist, but the reason I chose this topic is I have seen a lot of traction within Google and outside also around vector and how do I index it and what is the real life challenges we have. So it's not audible. Increase the volume, sir. Sorry, I've been speaking from yesterday and the booth, so a bit exhausted, but I'll try to do best. I will keep, as I said, interactive. I have this is okay. Yeah. Can you hear me now? Okay. So as I said, I'll just repeat. I'm not any data scientist or someone who can wrote some white papers on the how algorithms building and so on. But the reason I chose this topic is I saw a lot of people like me who do not understand this domain correctly. So I thought whatever I know, whatever we have done so far, and whatever we understood at Google side, I can share that across you. I kept it today's session specifically for what is available in the open source Postgres. I am not going to Google specific things. There are a couple of slides where I just wanted to show you what we have done improvement from Google side, but mostly all the content on the actual open source Postgres. So you can use it anywhere you want. This is nothing specific for the Google side. So with that, we can get started. I have some goodies to give also. So I'll ask you a few questions, not very deep, but feel free to answer, and then I'll hand it over the goodies to you. It's a nice one, so try your best. Okay, so let's get started. I hope this works. Yeah. So my name is Abhijeet. I'm part of the APAC data management practice based out of Singapore. I lead the data management practice for Google Cloud, and I've been participating in this event from last 4 years. So many of you familiar faces around, I see them. So yeah, happy to again here and interacting with all of you. Okay, so let's get started with today's topic. Few slides, bear with me. These are certain high levels, but we'll actually get into crux of it once we start seeing some screenshots. So as you can see here, why we are talking so much about vector and what is the significance of PG vector in overall things. Is it better? Yeah. Thank you. Sorry, you should have told me. Okay, so why this is important for all of us to understand the vector market, and I just this is a study done a few years back, but you can see that after the GenAI revolutions, whatever different LLM models got launched, be it Perplexity, DeepSeek, Gemini, ChatGPT, it actually growing exponentially. So that actually triggered the vector databases growth, and all of us here are going at some point during next few years, whether you use it today or no, there will be certain point that as a database professionals, we'll have to know what is vector, what are the different indexes options, and I'll not go into vector databases today because we are at the Postgres conference. So we have seen tremendous improvement within Postgres PG vector capability, and I'm sure this community will drive it further. So as you can see here, the market is expected conservatively up to more than $8 billion in almost 8 years' time. So this is again a conservative number, but yeah, we expect it to be much bigger. And if we focus on PG vector itself can drive certain amount of adoptions into the Postgres world, because then you don't have to go to specialized vector database. You can manage your operational data as well as the vector data side by side within the same database, right? So now, since all of us are a database background, what is important for us to understand is what database has a role to play in this GenAI world, right? So all enterprises are exploring GenAI use cases. It's not like they are live. Most of them are exploring. Some of them are live. Some of them are in certain areas like agents and so on. But mostly, what database role in this is, database will give you a context. So we hold the actual operation data. We know the inventory of any. For example, if you want to give someone a 10-year toy, and you ask a question to any LLM model, what toy I should gift. So what happens, it will just suggest you certain list of toys. But when you actually have a database connected to your question, then you know from where I'm asking the question, what is my customer ID, what store are near to me, and what is the inventory. So that data is residing in vector, in your, I would say, Postgres, and the inventory. So this gap between the actual LLM questions and with the data what we have will be filled by operational database. So we have a bigger role to play here because the inventory data will come from Postgres. The customer IDs finally will be stored in Postgres. So without that, just showing certain results will not be useful for any customers, right? So overall, we have a role to play here, and database actually bridge the gap between the large LLMs, different LLM models, and the GenAI applications. So now we established that. So how does PG vector comes into the picture? So as I said, with the PG vector capability within the Postgres, your operational data and the vector data sit side by side. So you don't have to go and do any other vector database. You don't have to join or ETL, move data across to have the vector embeddings in separate database, then your operational store in separate database. Everything sits together in the co-location. It's a familiar database technology. You can see it's a vibrant community we have here. And finally, it's open source. So that's very important as well. From Google side, we have two databases currently which support PG vector. We have Cloud SQL and we have already both supports PG vector today. And I am sure you are aware about these limitations, but to reiterate, 2K is the limitations on the embedding if we want to generate the index. I am sure this may not be applicable after a few years. Community will work, and next few releases of Postgres, this will go away. Other limitation around Postgres is it performance really degrades if at large scale. If I have billions and billions of vectors within the Postgres, it may, and performance can be a challenge. Yeah, and third is, I mean, we talked about the advantage, but there can be a disadvantage because your operational data is sitting side by side with your vector data. So if your vector queries load the database with too much, then your operational data querying gets suffered. So with that, let's understand what is embedding. Feel free to stop me if you, I'll pause for some questions afterwards in between as well. But essentially, though, for those, some of you understand this domain very well, but for those who wants to understand, it is what is the embedding? It is just a representation of any object type into the numbers, right? So that's what we call it embedding. What we have done here is we have embedded 3 different texts. 2 are positive and 1 is slightly negative feedback from customer sentiment point of view. So if you plot this embeddings onto the graph of sentiment versus satisfaction, you can see the green ones are first 2. Embeddings are on that side, top hand side, the quadrant, and then we have the blue dot here, which net product are damage. So this is what the embedding is all about. But it is not that simple as we see in the previous slide. So just wanted to give you context that how challenging embeddings can be. So these are the embeddings we did for 8 billion Stack Overflow questions. And this is how it looks like. So it's fairly challenging. It's for understanding purpose, we had the previous slide, but in multi-dimension space, embeddings can be challenging, and then searching them, navigating them becomes important. So why we included all this? Because then you can understand the importance of indexes in such a complex scenario, right? So now let's understand, we are talking today about the right-hand side, which is the serving index. But how do we reach there is you have different files of data, like whether it's audio, image, video, or text, any kind of data, you can give it to an embedding model. You can generate the embeddings in number format, and these formats will be stored in the vector database. And then you have the indexes on top of that so that you can search easily. So that's the end-to-end flow, a basic flow, but essentially you have the source data, you generate embeddings out of that, you store that into vector database or PG vector, using the PG vector extension within Postgres and inbuilt indexes on top of that. So now we saw the end-to-end flow. Let's move to the what are the why this is so important for all of us. Why everyone is talking about PG vector or search capabilities within vector. So these are certain use cases from day-to-day point of view. So you can say okay, what kind of content and document the image has. So you can search on this. You can search what are the products similar to this. I have some slides on that as well. And there is something like who are the users who behave like this users. And you can also do searching on that as well. Any other music of same taste and any other malfunctioning signals and so on. These are certain use cases. Obviously, these are not the full list, but just to get you understand the domain. Right. So, so you use your databases to store index vector embeddings using the large language models. You generate these embeddings and store into the database, and then you efficiently find similar items using the different search algorithms, right? And then you can leverage the relational database. So this is the simple terms PG vector extension within Postgres. So this is how you can use it basically. Right. So now I will introduce you to the next term, which is ANN and KNN. ANN stands for approximate nearest neighbors, and KNN is K nearest neighbors. So K stands for how many nodes or neighbors you want to have in the search. So vector, is a data type within Postgres. For those who are used to traditional indexes, vector indexes are very different. I'll show you some screenshots because I could not do the live demo because of the time restriction. I have some screenshots. I'll share it with you all. How these indexes are different. It's really a mind shift for anyone who is coming from traditional background that with a different index, your results can change. And I'll show you how it is. Yep. So if you don't create an index, so it always go for a brute force kind of a search algorithm in Postgres, and I'll show you that as well. By default, it performs the exact nearest neighbor search. So that's how ANN and KNN are important to us, and we will dive deeper into ANN because that's the indexing technique we are discussing today. Right. So what happens if I don't have an index on a database and I'm searching for a high heel shoe? This is my query item. So I uploaded this and generate an embedding out of this. So that embedding gets mapped with the existing embeddings within the database. So this is my shoe database, right? I have uploaded all my shoes images and generated embeddings out of that. So this embedding has to go one by one across these millions and billions of shoes and then find out what is similar to it, right? And then rank it. So it's a fairly expensive operation. Large millions and billions of items, it becomes infeasible as well. So that's why we need indexes, and because then you can actually zoom into exact area. And let me show you how. What are the types of indexes available for us today in PG vectors? So there are two types of indexes available. One is IVF flat and second is HNSW. So IVF flat is the old, although it's an old index type, but still useful. So it's not like always blindly go for HNSW, and I'll show you how well it is useful. And then the second is HNSW. So HNSW comes as the next version of NSW. So we had the navigable small world in the algorithm previously, but now they made it hierarchical. So now with the indexes, what happens? Previous example, the shoe which we try to search, understand that all high heel shoes are located here. Because if you see here, I don't know how many of you can see because this is not a proper stage, but all the high heel shoes are this side, then we have the sport shoe this side, and then the boots are this side. So we have that representation of different shoe type because of the way the embeddings are generated. And as the query comes, I know this is the area for high heel shoes. I'll just go here and then rank my results based on that. So I saved, if you remember the previous slides, so much navigations in my data. Right. So now we understand slightly, go deeper into IVF flat and HNSW. So we start with the IVF flat first. So as you can see here, what IVF flat does is it actually creates the cluster for number of, I would say, list of clusters basically. So it divides the data into different clusters using the list parameter, which we can specify while creating the index. And we'll show you that. So, I mean, we'll not go into these algorithms and white papers, but for you to understand what is this index is, you can control this list when you actually create the indexes. So I can say I want 100 lists, I want 1000 lists when we actually create the IVF flat. So it divides data into those clusters, and then when you actually get the query, you search that specific vector, you know which cluster to go in, and you find the nearest neighbor for that. Right? This is how IVF flat operates. Very simple implementation. It is very quick to build compared to HNSW. Uses less memory. That's I mean. So these are certain benefits of IVF flat. So as I said, it's even though it's an old technology, but it's kind of very useful in certain scenarios. Some of the limitations, you cannot have IVF flat index after without a data. Basically, what it does is existing data at the build time, it creates a cluster and divides them into the list. But if you don't have a data and you create index and then you load the data, it doesn't understand. So that's a big limitation. You'll have to rebuild the index after loading data, and there is a significant change in data. Right? So that's one limitation, because then it will not know how to calculate this cluster and these values. So yeah, if you don't know what your data sizes will be, IVF flat may not be the right choice. Then there's certain performance challenges as well compared to HNSW. It's slightly lower performing. You'll have to rebuild the index after the data changes. Right? So that's one of the limitations of IVF flat. Now let's understand the next index type, which is HNSW. And as I said, there was NSW algorithm, and then they add hierarchy on top of that. So it just been different layers. So I don't know, since I'm from Google, I can give an example of Google Maps. It's a you think of is as a state or city, and then you navigate to specific area. Say Yeshwanthpura, and so you start from Bangalore, and then you go to Yeshwanthpura, then you go to specific neighborhood, say Vijayanagar, whatever nearby. Yeah, so you start from a higher level, and then you go slightly deeper and deeper, and then you arrive at your exact search. So this will be your entry point, and this will be your layer 0, where you will find your exact results. Yeah, this is the HNSW technology, just simple way to understand for all of us. Right, so what are the areas or benefits for choosing this index over the IVF flat? So again, as I said, it's the most popular currently, and we'll spend most of the time here. So there is no training phase. That means even if you create the index and then load the data, that's fine. It is fine with HNSW, but not with IVF flat. Then what we can say is the tunable connections per layer, and so you can choose the M value, how many neighbors I want to give, you can choose in IVF flat at the time of creation. And then also you can choose how to search as well at the time of search. So what are the challenges with IVF flat? HNSW is, it consumes more storage and memory, because all these graphs get built into memory, right? While building the index, all these layers get built into the memory. Sometimes we have seen that the index size is more than the actual data. So that can be a challenge with IVF flat, and it takes a really long time to build an index. I mean, if you, based on the parameters, if you give higher parameters for M value, it takes a long time to build those indexes. Yeah. So these are the certain challenges for HNSW. So now we seen both the indexes, and I'm showing you a brief comparison. We discussed this in yesterday's training as well. But query speed, I mean, this is your kind of slide for just referring quickly. If you want better speed, HNSW is faster. Recall rate, recall is your matching, right? So how much matching I can achieve. So HNSW typically gives higher recall rate for same TPS, but it may not be true for all the data types. So it's really differs. So I don't want to, you cannot say, oh, Abhijeet said this is the best, but your data may be completely different. So please bear that in mind. If flat is the fastest index to build, suppose you've been asked to give a results on certain vector and you don't want to spend 8 hours for just building an index. You need to provide the results like within 15-20 minutes. Then obviously NSW cannot be the choice. You have to go with IO flat because it gets built quickly and you can provide results, right? We have the memory usage comparison as well, and IO flat is very low compared to HNSW. And then incremental data changes, as I said, IO flat is not suitable for where there is a lot of data changes. If your data changes frequently, then HNSW is the answer. Okay, great. So now we understood the HNSW and IO flat. Slightly, we'll go deeper. Yeah, so there are certain parameters at the time of index creation which we can say. So these two are parameters for, these are the three different types of, I would say, metrics which we can use while creating an index. You can specify this when create index command within Postgres, you can specify this. So you can specify vector cosine ops, you can specify L2, or you can specify inner product. So these are the three options, and let's try to understand which one to choose, right? So typically popular is this cosine, generally what everyone uses, but it may not be true for all the situations. So what does this mean? Cosine is basically, we saw certain vectors in the previous image plotted in that whatever that sandal example, right? The vectors plotted in a dense format. So cosine is essentially the angle between the two vectors, right? So it will not consider how far is that vector. I don't know, you are not able to see this, apologies, I thought it would be elevated stage. But essentially it will not, magnitude of the vector doesn't matter when you actually do the cosine, it just goes by the angle. So the less is the angle, its similarity is more. That's how it works, the cosine one. L2 distance is actually the distance between two vectors in the physics. So magnitude as well as the angle, both it considers when L2, you specify L2. And inner product is actually a kind of very similar to cosine, but it's actually give you both, like angle as well as the magnitude. Both are considered in the inner product. So choose based on your requirement. May not be the cosine may not be the right thing. So what are the measures? Similarity of direction angle for cosine, as I said, a straight line direction for L2. It is also called as equilibrium, direction plus magnitude, and then the projection of one to another. So it actually projects one vector to another, and that's called the inner product. So there are detailed formulas, may not be the right thing to go after lunch session, but for your practical use case, let's understand that these are the three options you can specify while creating an index, and typically people go with cosine one, but when to choose what is here. So generally works very good with text similarity, high dimension data. If you are normalized vector, this is the option to choose while creating the index. Then we have the geometric similarity, magnitude of vector is important. So how far is this one is what you need to consider. Then the L2 is the better choice. And similarly, inner product is similar to the cosine for normalized vector, but it is better in the relevance ranking. So these are the three choices you have while creating a HNSW. And I have a demo or screenshot for all three of these, and we'll see how it operates. Yeah. I hope it is not too much and you are with me. But think this as a create index, and then you in the bracket you have to mention one of these three options. Yeah. Right. So I'm ready to show you some slides. So For that, what I did, I did not have much time, but what I managed to do is I create an instance on a Cloud SQL, which is our flagship product in Google Cloud, which is open source Postgres, so you can do it anywhere, nothing to do with us. But 4 vCPU, 32 GB, some 17 GB of storage, and I loaded some 162K rows as embedding in this database. Yeah, this is my I would say lab kind of a setup. So I choose the deliberately slightly older version of Postgres so that in production you may have different versions. I know not everyone is updated today. So I use this setup to show you certain skills in the next few slides. So just keep in mind this is the database we talk about. And I created this table. This is a simple table where there is ID and title, and I created 2 vector columns here, vector 768. So you can have different dimensions of vector, but I choose the 768 for this lab purpose, right? So I embedded the title, which is here, and then I embedded the data. Yeah. So both vector data and data embedding, title and title embedding. So these two will be act as embedding columns. All are not null, so most of them are loaded with 162K. And there is a primary key on the ID. So simple table, not huge thing. So when I started creating IBF flat, what happens, right? So as soon as I started creating IBF flat with the list value of 1000. You remember I said IBF flat, there is a list, clusters, I can specify number of lists here. So if I just provide list value of 1000, my work memory gave me error, right? So my maintenance work memory is 64. For list to be 1000, it needs 351. So this parameter becomes very important when you actually want to create index or use indexes. Yeah, so please pay attention to this parameter. So obviously my operation failed. Then what I did, I modified that to list 100, and it created within how many seconds? 10 seconds, almost 11 seconds. Yeah. So that's how quick IBF flat is. I'll show you how much time HLSW took, and then we can have the comparison. But are we clear that I can reduce the list, my index memory size, as well as the build time also reduces. Obviously, it also compromises on search quality, so we have to strike a balance. Good. Now let's go to HNSW. So what I did is by default parameters. Sorry, it's not very clear. I know, but I'll try to explain. So we have 2 parameters when creating HNSW. One is M. M is nothing but how many neighbors. So if you are living in neighborhood, how many neighbors you have in your colony or whatever. Then EF construction is the list within that. It will search these many neighbors. So it acts as a list for that layer, right? We saw some layers previous slides, which for the HNSW. So you can control these parameters and create these type of index. So when I started creating this index, it says that it took 2 minutes on the same data. So I dropped the IBF flat and I created this index on the same data without specifying it. So by default, the current M is 16 and EF construction is 64. This is the time it took. Now, what I did, I increased my M value to 32 and the EF construction to 128, and it took me 7 minutes or 7.5 minutes. So you can see the change. I just doubled the value from 16 to 32 and 64 to 128, but my timing has increased exponentially. You can see the impact of increasing this, right? So it's not linear. So even I tried M64 and this 256, after 30 minutes it was still building. So that gives you the impact of these in your index building process, right? So choose these wisely, because sometimes you have to balance between accuracy and memory required as well as time to build the index. Just for if I want the best values, I cannot go with higher M values. We have certain guidance. I can share those with you towards the end of the slides. what values to be used for M and EF construction. Right? So it's not linear, it grows exponentially. That's the only thing. It So it depends on data as well. So tomorrow you run in your environment, you may not expect it to be 7 minutes. Based on your data, embedding time can be very huge or very less also, quicker. Right? So I also gave the CPU percentage, and obviously CPU percentage was higher when we actually moved the M values. Good. So you can see here when I actually build the index, I use the cosine, right? We studied about all three options. I use the cosine here. Now you may ask me that, okay, this is for cosine, what happens when I change it to L2 or IP inner product, right? So that experiment also I wanted to show you. So this is L2, so you can see L2 here, and this is inner product. So I just changed on the same data, I dropped the previous indexes and I created two indexes with the change option of algorithm. So L2 and IP, and you can see that the difference is not much. So that means the difference comes from M and EF, right? If you remember previous slide, let me go there. So EF construction and M, we did not specify, we kept it as it is. It took 2 minutes 12 seconds. Here also we haven't touched the EF or M value, it took 2 minutes. So your L2 or IP will not have significant impact. I will not say no impact, but significant impact on the build time. It will be driven by M values and EF construction. Is that point across all of us, right? So at least you should get something out of this session. So certain points I wanted to emphasize on. So it's driven by mostly these two parameters. Okay, so now we established that the inner product or the L2 distance is more or less similar. It's not like having huge impact on the build time. Now, what I wanted to show you is increase the, I would say, 32 and 128 for L2 and IP as well, because we did the same thing for cosine and the results are similar. So you can see it's about 8 minutes, it took 7 minutes, and in the previous slide, sorry, 2 minutes. So here also it took 7.5 minutes. So it's in the same range for higher ranges also. So that establishes that whether it's a cosine, L2 or a inner product, you will not have much significant impact unless we change the M value of the or the EF construction. Okay, are we okay here up to here? I think now. Okay, now is the first goodie time maybe. Can you anyone?
The EF construction should be higher than.
Okay, so I saw
M is lesser compared to EF.
Yeah,
It has to be double.
but I have only one. So what's your name? Sorry.
Naveen.
Naveen. Yeah. Can you come over? Thank you, Naveen. I think you spotted, right? Many of you spotted. My apologies. Sorry. Good. So although index may get created, I'm not saying index will not get created, but it doesn't make any sense. You cannot search within a limited period for larger nodes, right? So your EF construction is less than your M value. Absolutely no logic. Yeah. So now, other thing which I mentioned previously is if you are coming from traditional background, and unless you change your data, unless you change your where condition, your results will not change. Right? That's assumption from all of us from RDMS world, that unless my data changes, unless my where condition changes, or join changes, or query changes, my result will not change. Right? That's the understanding we have, which doesn't hold true in the vector world. Right? So your results changes substantially with index, with different types of index, with cosine, with L2, with IP, and without index, right? Because the way it has been built. So what I did is,
Would it give same result on each one, or that changes based on?
No, if your data is same and your index is same and your query is same, it will give you same query. But
Same
if you-
result.
Same result, sorry, same results. But if you change your indexes, if you change your data, or rebuild indexes, or change query, it will give you different index, different results. Sorry. Yeah, good question. So what I did, same query 2 times I executed with index, without index. You can see the difference. Nothing is common. It's a thing we have to understand, right? So even if I change my index type from cosine to something else, or HLSW to IVF flat, this will change. If I rebuild index after inserting some data, this result will change, and that's where it's called approximate ANN, right? All of us are clear. It is important for us to understand that my query, my data will not drive my results. It can be indexes also, and that's why we have to choose it properly. Yeah.
Just for clarification, this query saying whoever have published Delhi capital should their name publisher name.
Yeah, kind of. I mean, it's data is bit digitized here, so you may not be able to exact sense, but essentially that's the thing. So we are taking Delhi as an input, generating embedding using the model 005. So that embedding is getting matched with my existing data within this, and then results are getting produced. Yeah. So maybe you remember the table structure. I don't know. I'm using the same table structure for this as well. So this is my data embedding. So I'm comparing with this. Yeah. So if someone asks you how the results are different, there are many ways to investigate. These can be the reasons. Okay. Now we have seen the time of creation, certain parameters like M value and EF construction. There's something called IVF flat also, which we learned, which is list. So I show you a screen where initially it was 1000. I had memory issues, then I modified it to 100. My index got created. So how do we choose that? M values, and I have some. I don't know how much time we have. Sorry, she is not looking. How much?
5 minutes. Officially it's 4:15, but you can go.
Oh, okay. I hope you are liking, but yeah, I'll go slightly quick. But essentially, these are some values we have already seen. But what is the benefit if you go higher or lower, and what will be the cost of it? You can take a screenshot of this if you want. But this is based on the findings we did from the previous experiment, right? Okay. Then we seen at the creation time, but same thing is there for the runtime, right? When you execute your search, what are the things you can tune at the time of searching when you actually execute the query? So there is something called probe in the IVF flat. So you can specify this probe number. So you can set it at the start of the query, and that session will have those many probes. So you can set 1, you can set 5. So the more the probe, the more time, more accurate results you will get, but it also consumes a lot of time to get the results, right? And then we have similar parameter for HNSW, which is called EF search, which you specify at the runtime, not the build time. So let's not get confused. Build time is over. We have specified EF, we have specified the M values, we have specified the list, but now we are at the runtime. So runtime, it's probe and EF search, which is actually controls your recall rate, and also more the probe, your execution time will be more. Yeah, I'll give you some, I would say, ballpark numbers, what numbers to use as a practice, but let's not blindly follow it. That's what I say. Okay, so these are the typical values. M is typically these ranges for M when you actually create. Indexes for construction, we use start from 64 onwards and go up to 512. Target recall is your EF search, which is around 90, 95 is okay. That's the amount of matching you want to do, not 100%. List is 1000, but yeah, you can reduce it based on your requirement as well. And probe is 1 to 5. 5 is higher side, but yeah, this is good for, these two are for IVF flat, this is for HMS. Let's not get confused. Yeah, so these are certain reference ranges. Okay, so now how do I size my database for vector? Right? So when I generate an embedding, then I use a model, particular model, right? You saw 005 in previous slide. So that will have 768 kind of bytes. You have the OpenAI, which can have up to 1536. So we'll have to choose, our size will vary based on that. So a rough formula for that is dimension, which is like 768 into 4 plus 8. 8 is your PG vector overhead, where D is dimension. So whatever model you use to generate the embeddings, based on that, your vector data size will change. And on top of that, your index size is also there. So this is just a data size. So what model you use into 4 plus 8 is your vector column size. Obviously, other columns will have their own sizes, but this is standards on the vector because you may go wrong how much database size I require. Right. That brings us to the another question, and I have to get the box, but let me. Oh, I don't know who was. You okay? Can you please come? Your name, sir?
Ramesh.
Thank you, Ramesh. Thank you so much. Thank you. So quickly, as I said, I wanted to keep this very open source specific, so I just kept it to IVF flat and HNSW. But scan is something Google developed, but although it's Google thing, it's available on GitHub. So scan libraries are publicly available. You can go to this page here. Sorry about the height again, but it's available publicly as well. So it's, although Google developed the indexes and the library is there. So what we did is we have taken the ANN indexes and actually made it scalable, which is like because of the reason, obviously we have billions and billions of users across multiple services. So we wanted a scalable index better than HNSW. So we had scan. And this is what we included in our flagship product called AlaDB. I quickly share you some of the benchmark of the scan. So scan index is almost 4 times faster for vector queries. Index creation is 8 times better, almost 10 times in throughput, and less memory for 3 to 4 times. It varies, but this is just a based on our testing internally. Yeah. So if you compare scan with the HNSW, how it looks like, this is how the line for HNSW, and this is the line for scan indexes. You can see that the queries per second or the recall rate is significantly better with the scan indexes. Right. So with that, certain tips. One is memory. You saw the memory errors when we try to create the index. So one-tenth work made is important parameter when you actually create the indexes. Second is parallelization. How much max parallel workers, because now in Postgres, after 6.0, you can do parallelize the PG vector index creation, and then you keep on testing. I think that's the key here. So what are the importance points from day 2 operation point of view? I think obviously your RU index is getting used. Is your recall rate is drifting? I mean, your query results are really drifting than what was the initial intention. Then how my queries shapes change? I mean, how my queries itself have changed over the period, or there is a data drift, distribution changes for vector, or we have included new products category which has to be generated new embeddings, then my entire data set changes, right? So all these things we have to keep in mind for day 2 operations. And maybe one thing I forgot on the scan part, we have a target. You want to share something on your experience on this scan? Yeah, maybe introduce you.
Hi everyone, I'm Suman. So I'm from Target Corporation. Target is one of the biggest retailer in US, and we do have e-commerce presence which is growing year on year. So like our use case was to convert from full text search to vector search for our e-commerce website, and so we had a lot of challenges there. So initially we took a path of getting a purpose-built vector database, and we tried multiple purpose-built vector databases, but So as we start doing that, we learned that we cannot be part away from our operational data. So and because that become more challenging to integrate to achieve our required TPS and the other requirements. So then we tried obviously Postgres standalone instance, but HNSW. So we were not able to scale to the level which we wanted. And then we looked into the Google solution AlloyDB, with particularly with scan index, which worked really well for us. As I was saying, our use case was quite complex, where we had a lot of filtering, grouping, ranking operations, along with vector search on a very huge data set. And our latency requirements was like P99. We were looking for about 200 milliseconds, and we were looking for about 20K TPS, so which is really big during peak times. And this AlloyDB, obviously, it's powerful Postgres-backed database, which is very well customized by Google. And on top of that, we have scan index, which really worked well for us. So, which met all our requirements, and we are live with AlloyDB and scan for target search. So.
Excellent. Thank you so much. I mean, you can take this. I mean, just this was not rehearsed. I just met him outside and he said we are using AlloyDB. So thank you so much. Thank you. Thank you for this. Good. So now we understand the scan. We covered the day 2 operations. Okay. I think the last question here. I'm ran out of the Git, but I'll try to get something from the booth. Anything? Anyone? Yeah. Go ahead.
So we saw these two indexes are open source, and there is like scan from Google and then there's Vscan from Microsoft.
Correct.
They are proprietary.
Yeah.
Are there any plans in the community to add more or enhance?
Yeah,
this
yeah,
indexes?
absolutely. So scan library is already public in the GitHub. So there are certain plans. Google is planning to contribute heavily on the vector side, but yeah, that's the overall plan. Anyone? First, if anyone got this, yeah, go ahead. Sorry.
List or
Okay. No, that's not. Yes, go ahead.
There are multiple
Okay, that's the answer. So, thank you so much. What's your name? Shankar. Maybe I come to the booth, we'll have something for you. But essentially, for everyone's understanding, we created multiple types of index on the same data set, which will skew our queries like anything. It will not understand. So, if you see here, I'm using same column for creating 3 different indexes. There was a question yesterday that can I do that? I just wanted to show you can do that, but it is not helpful at all. Yeah. All right. So
is it possible to say which index to use at a time of query?
no, I mean unless you force it, but yeah. Oh, okay. Thank you so much all. Thank you. I hope it was useful. Thank you.